Those of you who were in the workshop earlier this week have already beaten this example to death. But it's just to give you a sense that, okay, here's an infinite family of graphs that have this desirable property of perfect state transfer. Okay, that's the good news. Okay, here comes the bad news. So this is a result from Chris Godsell, one of the collaborators on this paper. So for each natural number k, there are only finitely many graphs with maximum degree k for which perfect state transfer occurs. Okay, so that's a bit of a buzzkill, because what this is saying now is that somehow, even though we want this perfect state transfer, this desirable property, it's actually really rare. Okay, for each maximum degree k, you can find at most a finite number of graphs of max degree k that have this desirable property. Okay, so the takeaway from that is, despite an infinite family of nicely structured examples possessing the desirable property, in fact, it's rare. Okay, so so what I want to do now is kind of go back to the beginning again and rethink my approach to the notion of a state and to the notion of state transfer, because maybe if we think about things through a slightly different lens, we'll be able to generate larger families of graphs that have this desirable property. Okay, so I'm going to start all over again and redefine what a quantum state is. And what you'll see is that the stuff that I was telling you a few minutes ago is actually a special case of this broader context. Okay, a quantum state can be represented by a symmetric positive definite trace one matrix, D. D stands for density matrix. Okay, and this is a standard notion in quantum information theory. Okay, so let's think about a notion of perfect state transfer at time t between density matrices D1 and D2. And so the definition here is there is perfect state transfer between these two density matrices if I can, at time t, if I can write D2 as u of t times D1 times u of minus t. Okay. And so how does that connect up with what I was telling you about before with these vertices? Okay, well, the earlier notion of perfect state transfer from vertex J to vertex K is just looking at these two very special densities. Okay, D1 is the density matrix that I get by taking the outer product of E sub J with its transpose, and D2 is the outer product of E sub K with its transpose. So what you see is everything that I told you a couple of minutes ago about transferring information from a vertex to another lives inside this broader context of looking at transfer from one density matrix to another. Okay, and so basically what I want to do now is say, well, let's play with these ideas a little bit, and maybe we'll have more success in generating weighted graphs with perfect state transfer between these more general types of density matrices. Okay, all right, there's some words from the title. Now you're going to know what this means. Great. So a state is called pure if the corresponding density matrix has rank 1. Okay, in other words, I can take a unit vector z in Cn that has length 1, and I can write D as the outer product of z with z star. Okay, that's our pure density matrix, and D is a real state if all of its entries are real. Okay, and so in that setting, a real pure state can be written as the outer product of x with x transpose, where x is a real vector of length 1. Okay, and so that's what I want to focus on. I want to focus on trying to understand perfect state transfer between two real pure states. Okay. And so it's not very hard to work out, to sort of go back and forth between the vectors and the density matrices. There's perfect state transfer between real pure states if and only if they are unit vectors, real unit vectors, x and y, so that u of t times x is gamma times y, where gamma is some complex number of modulus 1. Okay. So as I'll say there's, despite the rarity of perfect state transfer between vertex states, there's still a substantial literature on that topic. And so that's really the case of looking at our x looks like E sub j and our y looks like E sub k. Right? And there's a growing literature on perfect state transfer for what are called pair and plus states. And so these are states that correspond to vectors like this. They're simple linear combinations of two standard unit basis vectors, either EJ plus EK or EJ minus EK, and then I multiply by 1 over root 2 to make sure that I've got unit length. Okay. And so these are all examples of real pure states. Okay, so the idea here is to take some of the literature that's already existing here and try and embed it in a larger context. Maybe something better will happen in terms of the frequency with which we can realize perfect state transfer. Okay. So again, those of you who are in the workshop will recognize some of the words that I'm about to use. Remember our Hamiltonian matrix M, so it's symmetric and it has a spectral decomposition. So I could write M as a sum from j equals 1 to k, lambda j, so lambda j is the eigenvalues of the Hamiltonian M, and E sub j, those are the eigenprojection matrices, okay? And so then, so if I write out our matrix M in that form and take a particular unit vector x in Rn, I can identify the corresponding eigenvalue support. I'll call it sigma sub x. And it's just identifies the eigenvalues, the lambda j's, so that when I look at the corresponding eigenprojection matrix and I multiply it onto x, I get a non-zero vector. So that's the support of the vector x, the eigenvalue support corresponding to this Hamiltonian in its spectral decomposition. Okay, so if I happen to have been given two unit vectors, real unit vectors, and they're not scalar multiples of each other. So y is not equal to either x or minus x. That's not an interesting case. And we say that x and y are what are called strongly co-spectral. If it happens to be the case that for each eigenvalue in the support of x, one of two things happens. Either when I look at the corresponding eigenprojection matrix multiplied onto y, that's the same as the eigenprojection matrix multiplied onto x, or it's minus the eigenprojection matrix multiplied onto. Okay, so they're strongly co-spectral if it happens to be the case that for each lambda in the support of x, when I take the eigenprojection matrix and multiply it onto y, I either get the corresponding version for x or minus that. Okay, that's the notion of strong co-spectrality. And if that's the case, then we can partition the support of x into two groups, two sets. Okay, it's the sets where EJY agrees with EJX, and the set where EJY is minus EJX. Okay, and I'm going to denote those by, what have I got there? Sigma xy plus for the plus sign and sigma xy minus for the minus sign. Okay. Again, if you've done perfect state transfer for vertex states, these notions will be familiar to you. They're the natural generalizations of what we need to talk about when we're going to these real pure states. Okay, so here's the question. I don't know, pick your favorite natural number n, okay? And now look inside of Rn and pick your two favorite vectors, x and y, make them unit vectors. And let's make things interesting. Let's suppose that x is not either, it's not y, and it's not minus y. Okay, it's not the interesting case. Okay, so two sort of genuinely different real vectors. And the question is, can I build a Hamiltonian that gives me perfect state transfer from x to y? The answer is yes. Okay. Sorry, this is the other, this is a related problem. Sorry about that. Let me go the other way. I've got a connected graph and I've got a Hamiltonian. Can I find perfect state transfer between real pure states? Sorry about that. The answer is yes. And the construction is, I'm almost embarrassed to tell you the proof. It's so easy, but it's instructive. So let's see. I've got my Hamiltonian M. So the M is going to have at least two distinct eigenvalues. Okay, so call them, so two of them, right? Lambda 1 and lambda 2. Lambda 1 bigger than lambda 2. And now pick a couple of unit eigenvectors, u1 and u2. So u1 goes with lambda 1, u2 goes with lambda 2. All right, and now I'm going to build x and y. All right, so x is going to be what I get when I add u1 to u2 and then normalize so that I have length 1. And y is going to be what I get when I subtract u2 from u1 and normalize. All right, and now I'm going to take readout time t naught, and it's pi over lambda 1 minus lambda 2. Okay, now let's just watch what happens when we multiply by that matrix u of t naught. Let's see what happens. Here we go. U of t naught times x is easily seen to be, so here's a complex number of modulus 1, okay? And it's the same as that complex number times u1 plus e to the I t naught lambda 1 minus 2 lambda 2 times u2 divided by root 2. And now, by the way that we picked the value of t naught is pi over lambda 1 minus lambda 2. And so when I evaluate here, I'll pick up a minus sign, all right? And I land on e to the I t naught lambda 1 times y. Okay, so what's the takeaway from that? I'm saying take any symmetric Hamiltonian matrix M that respects your graph. Okay, you can find perfect state transfer between real pure states. Moreover, I can tell you how to build it in a simple way like this. Okay, and there's sort of a little bit more good news coming out of this. This construction that I came up with here, that I just picked two eigenvalues that are distinct from each other and one eigenvector from each of them. Okay, now I have, in general, lots of different choices of pairs of eigenvalues and lots of different choices of eigenvectors that go with those eigenvalues, okay? So there's a bit of flexibility in the constructions that I can come up with for different choices of both the eigenvalues and the corresponding eigenvectors that come out.
Why should you take a connected graph? Just you take a M with the two distinct eigenvalues, then the proof will work.
Sorry?
Why do you consider a connected graph? Just start with a matrix M with at least two distinct eigenvalues, then the proof will work.
For sure, yeah, absolutely. Yeah. But I mean, there is, in my view, there is no difference between a connected weighted graph and a symmetric matrix M. They are equivalent in some sense. Yeah, but you're right. I mean, it really comes down to the fact that there are two distinct eigenvalues available. Off we go. Okay, so that's one good example or one good construction. Right, I want to go the other way now, and this is what I was trying to talk about earlier. So imagine that we've been given a pair of unit vectors, x and y in Rn, and let's take y to be neither x nor minus x. Okay, and while we're at it, I'll let you pick your favorite readout time, t sub 0. Okay, so have all those given, and suppose that we're also been handed some natural numbers m1 and m2, so that the sum of m1 and m2 is bounded above by n. Okay, then I can construct a real symmetric Hamiltonian matrix M that gives me perfect state transfer between X and Y at time t sub 0. Moreover, I can arrange it so that the cardinality of the positive part of the support between X and Y is M1, and the cardinality of the negative part of the support is M2. Okay, so I'll tell you kind of how the construction works, but observe that this is actually pretty good news, right? I can take my favorite states, okay, the X and the Y. I can pick my favorite readout time, and I can somehow build the matrix M that will give me perfect state transfer between the real pure state that corresponds to X and the real pure state that corresponds to Y. All right. So here's the setup. So I'm going to build some. Some matrices and some vectors. So let's see. I'll make a vector U1 that I get by taking M1. Remember that was one of the parameters that was given to us. M1 ones followed by n minus M1 zeros, and I normalize it to its length, so it has length 1. And then I build another vector, U sub 2. I'll start off with M1 zeros. I'll follow with M2 ones, and then I flesh out the rest with zeros, normalize so it has length 1. Okay. And then I'll build a matrix V1 by taking X plus Y and normalizing, and a matrix V2 by taking X minus Y and normalizing. Okay. And so the thing to observe is that U1 and U2 are orthogonal to each other, and they both have unit length. Okay, and so if I feel like it, I can just complete an orthonormal basis of Rn by starting out with U1, U2, and then just fill out the rest of the orthonormal basis. Okay. And same idea here. Observe that the way I built the V1 and the V2, those two vectors are also orthonormal. Okay, and so I can do the same trick. Start with V1, follow it with V2, and then build some rest of a orthonormal basis that starts with V1 and V2. Okay, so my first orthonormal basis, I'm going to put the columns into a matrix called Q1. The second orthonormal basis, I'll place those in the columns of Q2. Of course, Q1 and Q2 orthogonal matrices. All right. And so what do I do? Well, I'm going to build this orthogonal matrix, Q2 times Q1 transpose, and I'm going to name the columns of that matrix as W1, W2 down to Wn. And by the way that we set everything up, well, we started the orthonormal basis with Q1 and then followed it with a special construction for Q2. It turns out that there are non-zero scalars, C1 and C2, so that our vector X that we started with is C1 times the sum of the first M1 columns, the W1 through WM1, plus C2 times the next M2 columns in that matrix. All right, that's what X looks like. Y looks like almost the same thing, except that there's a minus sign sitting in front of the second summation. Okay, and so now what I want to do is construct a Hamiltonian of the form M is equal to a sum from j equals 1 to n, theta sub j, so theta sub j is a scalar, times wj transpose. So basically what I'm doing here is I'm building the matrix M through an eigendecomposition. The eigenvectors are the wj's, the eigenvalues are the theta j's. And here's the thing to note, by the way that we organized all of this stuff, the vectors X and Y are strongly cospectral with respect to the matrix M, and that sigma plus and sigma minus for XY have the desired cardinalities, right? We wanted the first one to have cardinality M1 and the second one to have cardinality M2. Now, I'm hiding something here. Okay, I've been very explicit about the entire construction here, except I didn't tell you how to pick the theta j's. And so the scalars, the eigenvalues of the matrix that I'm trying to build, have to be artfully chosen. Okay. Now, I'm not going to leave you hanging there. So what the heck does artfully mean? So here's the result. Maybe even don't read it here. Okay. I'll try and describe in general terms what's going on here. So if I've got a graph on n vertices, I've got my vectors x and y. Y is not equal to plus or minus x. So there are two cases to consider. So if sigma x, the support of the vector x, if that's 2, then it turns out that x and y give us perfect state transfer with this Hamiltonian matrix M, exactly in the case that they are strongly co-spectral. Okay, that's kind of what we have seen something similar before. Otherwise, we let the sigma x be the lambda 1 through lambda m. Okay, so these are the eigenvalues in the support of the vector x. The vectors x and y admit perfect state transfer if and only if x and y are strongly cospectral. That when I look at this fraction here, lambda 1 minus lambda j and lambda 1 minus lambda 2, for each j at least 3, that can be written as a rational number, pj over qj, where these are the p's and the q's are relatively prime integers. And then there has to be a special condition that holds with respect to these things. So if lambda 1 and lambda 2 are in sigma plus, then let's see, nu2. So nu2 is the largest power of 2 that divides the integer q sub l. Okay, I want the nu2 of ql to be equal to the nu2 of qk and to be bigger than the nu2 of qh for each pair of eigenvalues, lambda L and lambda K in the sigma minus part and lambda K H in the sigma plus part, deleting lambda 1 and lambda 2. In addition, if lambda 1 is in the positive part of the support and lambda 2 is in the negative part of the support, then each Qj is odd. Each pH is even, provided that the lambda H is in sigma plus. And here's the minimum PST time, where Q is 1 in A part, and Q is the least common multiple of Q3 to Qm in the B part. Okay. So that's a lot of information to take in, but here's what I'm telling you. If you sort of don't worry about the details, this is a characterization of what the relations that the eigenvalues in the support of x have to obey. But the point is, to go back to my earlier thing about artfully chosen, what you can do is go in and pick the theta j's to satisfy this list of conditions. It's not very hard to do. Okay, you have a lot of freedom for the theta j's. You just set it up so that all of these conditions push through. Okay. All right. So takeaway from that is I can. Do I have it on the slide here? Nope, I don't. The takeaway from that is I can pick my favorite two vectors, x and y. I can pick my favorite readout time, t naught, and I can build a Hamiltonian that gives me perfect state transfer between the corresponding real pure states that go with x and y. Okay, good. Just as an example, we can think about paths. We can think about the path on n vertices p sub n. And so when we use the adjacency matrix as a Hamiltonian, there's perfect state transfer between vertex states, so this EJ and EK business, only for paths of short length, n equals 2 and 3. And so we want to see if we can get perfect state transfer for other types of real pure states using path Pn. And so I'll just, these are well known for not just people working in spectral graph theory, but anybody who knows stuff about orthogonal polynomials. For the adjacency matrix of the path on n vertices, these are what the eigenvalues look like, and the corresponding eigenvectors look like this, is built out of trigonometric functions. And so here's an example of a theorem you can prove. So using the adjacency matrix for the path on n vertices. So suppose I've got a couple of vertices, sorry, a couple of vectors, x and y in Rn, take them to be, unit size. Sigma x is at least 3, and for technical reasons, I'll ask for sigma x to be closed under algebraic conjugates. Then P sub n admits perfect state transfer between x and y if and only if. And again, I don't think I even want you to read out the slide, or I'll just say if and only if something nice happens with the value of n. Okay, and the x and the y are built very carefully out of certain eigenvectors. Okay, so in the first guy, it's Z3m, 2m, and 4m. Z3m, Zm, and Z5m. And in the second case, it's Z2m, Zn, and Z3m. And you've got some flexibility, some parameters here, the A, B, and C that can be chosen. And you know the readout times. So, let's see, in the first case, in 1a and 1b, and in 2, the readout times are pi over 2, pi over root 3, and pi over root 2. Okay? So all I'm doing is saying here, you can take a particular graph, P sub n, that might be desirable to work with, invoke the theorem that I gave you about the artfully chosen eigenvalues, and decide which vectors x and y will admit perfect state transfer using this particular Hamiltonian. Okay. I'll talk a little bit about readout times. Notice that if you read that big horrible theorem, sort of the punchline at the end of it was our readout times are of the form pi times some integer divided by the difference of two eigenvalues. All the readout times look like that. And so I just want to talk about trying to get the readout times as small as possible for practical considerations. If I want this perfect state transfer to happen inside of a quantum computer, I do not want to have to wait very long for the correct readout time. Otherwise, I lose the advantage of whatever quantum speedup is available. Yeah? Okay. So if we're using the Laplacian matrix of order n as the Hamiltonian, it's well known that the smallest eigenvalue of the Laplacian is 0, and that all of the Laplacian eigenvalues are bounded above by n. It's also known when we take n as an eigenvalue. It's when the graph is a join, and that means that so the join is just what I get by taking two graphs, G1 and G2, and adding all possible edges in between them. And so what we're saying here is, for the Laplacian matrix, the smallest possible readout time is pi over n. It's attained precisely when the graph is a join, and 5 minutes? 3 minutes, cool, thanks. And we can characterize the vectors x and y that realize this perfect state transfer at the minimum PST time, pi over n. Okay, so that's when we're working with a Laplacian matrix. For the adjacency matrix, we can go through a similar analysis. It turns out the graph that maximizes the difference between the largest eigenvalue and the smallest eigenvalue of the adjacency matrix is the join of an empty graph on n over 3 vertices and a complete graph on roughly 2 over 3 vertices. And again, as I said before, we're able to precisely characterize the vectors x and y that realize this perfect state transfer of pi over lambda max minus lambda min. I'll just give you the formulas. Again, don't read it too carefully, but basically observe that the vectors that I'm looking at, the x and the y, are built, they're linear combinations that are built out of vectors that are all ones on the first part of the join and a different multiple of the all ones on the second part of the join. Okay. I had a little bit more to say about readout times and sensitivity, but I think I'm going to buzz through that so that we have time for questions. And I'll just move to the conclusion here. There's a tension around the quantity lambda max minus lambda min. Okay, on the one hand, the minimum PST time can be made small if lambda max minus lambda min is big. On the other hand, we didn't have time to tell you this, if lambda max minus lambda min is large, then the sensitivity of the fidelity with respect to the readout time can be large. We can, if we relax a little bit to perfect state transfer between two real vectors, that gives us a much wider family of Hamiltonians, and we can get them to have PST at our favorite readout time. And that there's lots of different ways of constructing those Hamiltonians if we like. So it would be interesting to explore constructions that have other desirable properties. Maybe you'd like your Hamiltonian to be entry-wise non-negative or sparse or with integer entries, etc. So I guess what I'm saying is that there's lots more room for exploration on this topic. Thank you for your attention.
Thank you. Any questions, please? Yes.
Sir, it is a nice talk. So my question is, what can we think of in case of join of graphs if these vectors are not perpendicular to one? Because in this case, we consider 1 transpose x1 equal to 1 transpose x2. So if it is not perpendicular to 1, then what can we say?
Talking about the Laplacian matrix?
Yes, it is Laplacian, or in case of regular, it is adjacency. So.
Right. Yeah, I'm not sure. I think, as I said, there's lots of room for exploration here, and so that's a perfectly good thing to think about. Yeah.
Okay, sir.
Any other question? Please.
In
Any
your
other question?
theorem that T doesn't appear, why?
Sorry?
T, U of T, in your
Yeah.
theorems, path and all, T doesn't appear, why?
So when we were talking about the path,
Yeah, path.
so the readout times
Right,
were
sir.
given right at the bottom. So I think I said it was pi over 2, pi over root 2, and pi over root 3.
Oh,
So for those particular, so the x and the y have to have a special form, and the readout time came up as. Yeah.
Any other question? Can I ask something myself? Can you give me one example where this commonly applies? Where you can apply this?
The construction.
Yeah. Why am I doing this? I'm a theoretical mathematician.
Yeah.
So I'm very curious to see that this is a very interesting.
Yeah, so I want to build a quantum spin network that transfers quantum information from one spot to the other at a good time. And the reason I want to do that is I want to use that as data bus inside a quantum computer, okay, to transfer quantum information from one spot to the other. And so having these constructions where I can keep control of the readout time and know where to look, what state to look for to put in and to read out. These are desirable things.
Can you tell me one practical example? Where will you be using it?
I mean the thing's been realized in the lab. Is that what you mean?
No, yourself. You are using these matrices
Yes.
for some dynamical state, right?
Yeah, for a quantum state.
Yeah, quantum state.
Yeah.
So I'm sure there's a question which I want to apply it for. I mean, practical life.
Yeah.
Where I can say that. What can I do?
Where can you find the right question?
Yeah,
Okay, I'm going to
practical.
direct you to the seminal paper of Sagatu Bose from 2003. And so it's the sort of the grandfather of this line of work.
I see. Okay.
And it's the attempt to pass a quantum state from one part of one endpoint of the path, the other endpoint of the path as a data bus.
Okay. Thank you very much for a very comprehensive, very interesting lecture. Thank you for coming and giving this talk. Again, thank you very much. Bye. Our next talk will be in about 10 minutes. Am I right? That will be at what time is that? 10:50. 10. What time? That will already. Oh, it's already 10:15, so no 10 minutes break. So the next speaker is Professor Andre Leroy from France. He happens to be my co-author, co-worker with me, who is has done various kind of work in ring theory, module theory, linear algebra, combinatorics, and everything. So I'm pleased to introduce him. He is going to speak on, let us see what is the name of that is, on the pseudo-linear maps. Pseudo-linear maps.
Okay, good morning. Thank you for the presentation. So yes, my young friend Iclaa Jane. I need your help. My voice is it better? Okay, I try. Thank you. Yeah, it's a pleasure to be here, and this is the fourth time I'm here, and I am enjoying every moment. So thank you for your smile and for your welcome. Very warm actually, even by the weather. So today I will speak about pseudolinear maps. In fact, this talk it's kind of survey, and it could be also called pseudolinear and evaluation of polynomials in a non-commutative setting. So quickly, I will just go to the classical case, skew polynomial rings, where I will introduce them, and then I will get the definition of pseudolinear, the transformation, the evaluations, and the roots. They are they are strongly connected, and then we will go to the case of n variable, and at the end, I will give a recent application to a question which was asked by my I'm sorry. It's my usual problem. Oh, shoot.
That'd be better to speak it louder because, yes.
Okay. Okay, so let's try. Yeah, so we will see anyway what should be going on. So the first thing is I want to introduce the pseudolinear maps. So everyone knows what a linear map is, but there are many ways of introducing the pseudolinear one. One way is just to say, okay, when you have a linear map, you have also on your vector space, you have also a polynomial structure, a module over the polynomial ring, right? So when the action of K, so you assume you have a vector space V over K, and you have a linear map T, and then this V can become a KX module, as everyone knows, by an X acts on V, just like T. And so you have a module over KX. And we will do the same, but instead of using just the usual polynomial ring, we will use the skew polynomial ring. The skew polynomial rings were introduced by, let's say, formally by Ore in 1933, time ago. And a few years after, in 1937, Jacobson introduced the pseudolinear transformation. So what's a skew polynomial ring, and why introduce them? Well, in fact, when you work with a base ring, even for the usual polynomial, when you want to evaluate, you see that there is a problem, because since your base ring is not commutative, if you take x, a variable which commutes with the scalars, you have a problem. For instance, if you take ix, so assume you have h, the Hamiltonian quaternion of Hamilton, and you take Ix if you want to, Ix is xi. But then if you evaluate a j, then you have a problem there, right? So you have a right evaluation, left evaluation, and so on. So starting with this, and honestly, it's rather the motivation under the introduction of the skew polynomial ring is rather on the side of the differential equation seen on the algebraic point of view. Because if you think about it, the left multiplication by an element and the derivation, if you have a derivation of on your ring, they don't commute, and they follow a rule which is given, for instance, transparent in the Weyl algebra. Okay, so now if you have a ring, now I'll start formally, just like OA did. You start with a ring and an endomorphism, and you have a map which is a sigma derivation. What's a sigma derivation? Well, it looks like a derivation, but it's just it's additive, but it's not multiplicative. Well, it doesn't follow the Leibniz roots. It's a special one. So you in the for delta acting on a product, you have that of AB as just sigma A delta B plus delta AB. And you see, it's not symmetric actually. You can also have tau sigma derivation and so on. But we will just work with this because they arrive naturally if you work in some frame, they arrive naturally when you look at a non-commutative polynomials. By non-commutative, I mean that, of course, that the base ring is any ring with one. I don't like it. Okay. But I don't assume that the variable is commuting with the scalars. Okay. So, and the commutation rule is this one. And when I say this construction appear naturally, assume you have a domain. So you have a ring which has no zero divisor, and you want to construct the polynomials for the you want to look at polynomials. Polynomials you write them with the coefficients on the left, and you assume you have unicity of this. And then when you have TA, you have to pass over, and so you have some kind of map here. And when you look at associativity, you will see that the sigma must be an endomorphism and delta must be a sigma derivation. That's all. So this is a way of doing it. So some example, very simple. So you take C and then you take the conjugation. There, the thing is very simple. You pass through T by applying conjugation. So for instance, if you take Ti, you have minus IT. The next example, if you take FQ, just the finite field with Pn element, and you take theta as the Frobenius map, and then of course, well, you can have you have the commutation rule that TA is APT, A to the P times T. Okay, and this kind of rings, they are used very often in coding theory nowadays. Because in coding, what they offer, why is it so important? Why they are important in coding theory? Because the factorization is, there are many factorizations. So if you take a polynomial, and then you can factorize in many ways. Okay. This will have some impact also on the number of roots. I will come back to this later. So these are used, and why is it important to have a lot of factorization? Because in fact, when you look at linear codes, and when you divide by something like well, a polynomial, what you will look is you take the quotient, or you take a central polynomial if you want, and you take the quotient, and the codes will correspond to the factorization of your quotient. One thing I have to say here is that this polynomial is in fact a left and right principal ideal domain. Okay. The next example is just the Weyl algebra. The Weyl algebra, you take kx and then you take the identity as sigma, and you have just the usual derivation with respect to x. So if you take this and then you have tx, so here you have to pass x through t, but this is with the identity, so you have tx as xt plus, and then the derivation of x with respect to the usual derivation, so it's 1. So this is the Well algebra. You can iterate this. In characteristic 0, you have a nice simple range. If its characteristic is not 0, then the center is big. Substance, okay. Now, give me, well, I guess you want to have some example of sigma derivation. This is the strange things here. Well, you can take, of course, the sigma inner derivation. So you fix an A in your ring, and then you have sigma. So sigma is just an endomorphism ring. And you have this gives you a sigma derivation. So ax minus sigma xa. If sigma is 1, you just have the usual inner derivation, right? Okay, and then you will ask, well, can you have non-inner derivation? Yes, I give you here one, two, yeah. The fact is that when you have a an inner sigma derivation, in some sense in the polynomial ring, by changing the variable, you can erase it. Okay, so this is, but sometimes you cannot because the derivation is not inner. Okay. So now I come to the pseudo-linear transformation, PLT, as I will say. You assume you have your ring, your endomorphism, your sigma derivation, and you take V a left A module. So your base ring, right? A is your base ring. An additive map from V to V. So it's additive, so T of A plus T of V1 plus V2 is T of V1 plus T of V2, okay? But you don't assume that it's homogeneous. So in the sense that T of alpha V, if it's linear, then it's alpha T of V. But it's not linear, it's pseudo-linear. And this is given by sigma alpha TV plus delta V. Plus delta alpha V, sorry. Delta alpha V. Okay, so in particular, if you take delta is 0, if you take the usual polynomial ring, then you have this delta is 0, sigma is 1, so you have just the linear maps. Okay, and in fact, can you go down a bit? Thank you. Yeah, okay, yeah, sure. Okay, yeah, that's okay. So, in fact, there is a 1-1 correspondence. When you have a left A module and you have a pseudo-linear transformation, you get an RP module because you have the action of T, the PLT, and correspondingly, every time you have an R in R is just AT sigma delta, right? When you have your ring R and you have a left R module, it's a left A module, and the action of small t, the indeterminate, give you a PLT. So it's really like in the usual case. Okay, so there is so there is a nice thing with this PLT when you have a pseudo-linear transformation. You automatically get a map from your skew polynomial ring into the additive endomorphism of your vector space. And it's really a ring endomorphism. So you have fg of t as f of t, g of t. What means f of t, for instance, f of capital T? Well, you have your polynomial f of small t, the variable, and you replace the small t by capital T. Just this usual thing. So the square, so small t square is sent to capital T square. Just replacing the capital T by the small t. Yeah. Okay. Yeah. So just to go on. Yeah. So okay. So we have this. Yes. And here, as this is what I said. A left R module is just a left A module plus the PLT. So there is a 1-1 correspondence. Yeah. Go down. Okay, if you take the first example of a pseudolinear transformation is the derivation itself. So if you consider A as a left A module, you have the derivation, delta, and it's indeed sigma delta PLT over A. A considered as an A module. Now, there is a very another classical way of getting PLT is just when you have, once again, from A to A, you pick any element A in your ring A, and you define Tx as this with this thing. Ta of X is just sigma X A plus delta X. Look at in the case delta is 0 and sigma is 1, this Ta is just the right multiplication by A, nothing else. So, and this kind of pseudolinear transformation is in some sense generic. It's just they are, when you are working with a free module, they are all of this type. Because when you have a free module, you will attach, as in the linear case, when you have a linear map and a vector space, you take a basis and then you have the matrix of the linear map into this basis. You can do the same thing, but there are some things to take care. I will come back to this later. Here I'm just writing that, for instance, giving some place where this pseudolinear transformation have some importance. If you take delta as 0, you get the semilinear maps. Right? This is what we call semilinear maps, and they play a very important role in projective geometry because they preserve collineation. Right? So if two vectors are collinear, then the image by PLT is also collinear. So you have not only the linear map and divided by the PGLV is just the GLV divided by the center, but this doesn't give you all the projective maps. You have also the one which are, if your base field, for instance, you can take C and then the conjugation. So there are other project coordination. Yeah, the second one is I don't know too much. You will see. I just at the end of the talk a very long bibliography, and it's my intention to transfer this talk to the organizers. So if you want it, you can call them, you can ask them, or you can ask me, of course. So there is a very long bibliography, and in this very long bibliography, there are some books, notably the book by Henri Bourles about time-varying system, and there he's using the skew polymer ring and the PLT. Yeah, the PLT also they are attached to pseudo linear extensions, and they were used by PM Cohn to have a strange behavior of division rings with left and right dimension different. Okay. Yeah, and what we will be interested in essentially is the relation with the pseudolinear transformation and the evaluation of the polynomials. Yeah. So there are some things you have to be careful. If you have a linear map, if you compose it, it's still linear. Here it's not true, of course. Here is the law. For instance, if you take even T composed with itself, it will not give a PLT, but you have, of course, some way of computing it, of computing the Tn of alpha V. There is another thing which is a bit, there are many things, but another important one is if you think about it, if you take delta derivation, so sigma derivation, so you have your, consider A as a left A module, you can take 1, the element 1 as a base, and then delta of 1 is 0. So the matrix associated to delta is just 0, right? So, but of course, this doesn't mean that delta is 0, even it's. Yeah, here are a few technical things. I think I can more or less. Yeah, of course you can, as I said, you can, whenever you have a vector space and a basis, you will have a matrix associated. Yeah, let's go down a bit. Yeah. Just I want when you change the variable, sorry, when you change the basis, there there is a change of basis formula, but it's a bit different than the usual one. Okay, and yeah, here when you look, so you take P. First is R is just AT sigma delta, right? So your polynomial ring, your skew polynomial ring. You take P inside, and then you can look at R over RP. And the endomorphism of this is what is called the eigenvalue. It's isomorphic to the idealizer divided by RP. And here it says a very concrete description in terms of this matrix C is just a companion matrix. Okay, let's go down. Let's go down. Let's go down. Yeah. Oh, yeah. Here, if you have beta basis of your vector space, and then you take f of t, so f is just a skew polynomial. You replace the small t by capital T, and you look at the basis. So it's a map, right? This will be a map from V to V, and you can look at the matrix. And so if you take ft of beta, it's just f of t beta. But this f of t beta, so here ft is a map. You look at its matrix in the base beta. Here you have t beta. This is the matrix of t in the basis beta. And then you take f, but there is an equality. But this equality, this f is not, you evaluate f at t beta, but not in the usual sense. You evaluate because your polynomial is don't forget, it's a skew polynomial. So the t and a, the constants and the variable t don't compute. So we have to define what is meant here and how to compute it. Okay, so let's go and you take your polynomial ring, AT sigma delta, and you take your polynomial, and you want to just to evaluate. How can you do this? Well, as usual, if you have a PT of a polynomial and you want to evaluate at A, you just look at R over RT minus A, and you take the remainder, right? You divide T by T minus A on the right, you take the remainder. This will be what you call the evaluation, right? So if you take some example, just take T squared, and I want to evaluate at A. The classical evaluation is just A squared, right? Here, the variable doesn't commute. So what I do, I just try to write T squared, I should, yeah. Okay, so it's t squared as t minus a plus ta. So you have to forget about the a. So t squared as t minus a plus ta. And then you try to push ta on the right. So first you have to switch the a and the t. So you have sigma a t plus delta a. And then replace the t which is there by t minus a. And finally, you see that t squared evaluated at a is just sigma a plus delta a. Of course, if delta is 0, sigma is 1, you have just a squared. And you can continue like this. And in general, of course, to evaluate a polynomial, you just have to know how to evaluate the powers. So this is called the NI, and you have an induction formula, but we can skip this. So what's the relation between, what's the relation between the evaluation and the PLT? Well, the connection is via the PLT, the pseudolinear transformation T index A. We call that T index A as just sigma XA plus delta X. Okay. And here is the connection FT at A, FTA at 1. Here, the FTA is just I replace small t by capital T. So it's not okay. It's not evaluated. It's not evaluated really. FTA at 1 is just FA. So F evaluating F and computing FTA are very strongly related by this. And if you remember, we had the we knew that there is a ring homomorphism between the array extension and the endomorphism. So we knew that Fg applied to T, capital T, is just Ft GT. And using this, you have this nice product formula. Fg evaluated at A is Fta at Ga. So this gives away, and remember, the ring A is just any ring, not a field or division ring, or just any ring, and you still are able to compute this. Okay, but if you are lucky and X is a unit, then Fx of A is Fax, right? I assume that X is a unit, then I can compute this. But then you will say, but what is this Ax? This Ax is just the sigma, it's a conjugation of A by X. X is a unit. So classically, the conjugation A by X is X, A, X inverse. Here, the sigma and the delta will be involved. So so in other words, to compute Fx of A, you have to involve the conjugation class, conjugacy classes. Sorry. Now, we have seen, we have this relation, Fa is Fta at 1, so you can, and this also, so you can see that the kernel of Fta will play a special role, and so the kernel of Fta is just there. Yeah. Yeah, here is, so when you have, so let's take a division ring as a base ring. And then you have an array extension, kt sigma delta. K is my division ring. Okay. And you can, of course, you can take sigma is 1, delta is 0. So you have a usual polynomial over a division ring. So how do you compute the roots of your polynomial? First thing, K is a division ring, so it's not commutative. For instance, we can take H. You can have much more roots than the degree, much more. And the second thing is that you, instead of working with trying to bound the number of roots by just counting the roots, you just glue the roots together when they are in the same conjugacy class. This was a theorem by Gordon and Motzkin in '65. So they said the following: you take the usual polynomial kx over a division ring. The number of roots of f is bounded by the number of conjugacy classes that contains a root. So you have f, you have vf, the set of roots. You divide vf into conjugacy classes, and you count the number of conjugacy classes that are concerned with their roots as bounded by the degree. This was in '65. Now, a few years later, let's say, we have a better bound. What is going on is that you divide again your roots. And first of all, this was done in '65 in the case sigma and delta is 1, delta is 0. But it's also for the array polynomial ring. So if you take a polynomial ring with sigma and delta non-trivial, then you still have the number of conjugacy classes is bounded by, concerned by the roots is bounded by the degree. Here it's the sigma delta conjugacy classes. But you have more. If you look at the kernel of, so assume you have an element which is a root. So the conjugacy class is delta A, we call it delta A, and you can look at Ft index A, and you can look at the kernel. And this kernel, it's a vector space over the centralizer, the sigma delta centralizer. And so you have the sigma delta centralizer when K is a division ring, it's a division ring also. And so you have the kernel of FTA. It has a dimension over the centralizer. And now you have VF, so the set of roots divided in conjugacy classes, sigma delta conjugacy classes. You look for each intersection of the roots with the kernel of FTA, and you take the dimension. You sum all the dimension, and the sum of all dimension is bounded by the degree, so it's much stronger. Okay, yeah. So you can go down maybe. Yeah. So of course, in the case you have a division ring as a vector as a base ring, the things are a bit easier, and you have many things which are classical, like the eigenvalue, the diagonalizability, this kind of things. This happens also. This happens especially when you assume that your sigma delta pseudolinear transformation is algebraic. Of course, it's not the case in general, right? If you take a vector space and a linear map, well, it's algebraic, no problem. Here, it's not the case. Even very simple. You take a division ring element, and you consider it as a left vector space over itself, and then you have the delta. The delta itself is not necessarily algebraic, right? So, but when it's algebraic, everything goes on smoothly and very similar to the classical things you can go. Yeah. Yeah. So you can. Yeah. I will just go there if you don't mind. This. Yeah. Okay. Yeah. So if I want to be quick, it's like this. Yeah. Let me give you quickly, if you take FQT, for instance, you can find a polynomial. So FQX, classical thing, X is a commuting variable, T is not commuting, right? Okay, FQX, you have X to the Q minus X, which is very important for polynomial, right? And you have a similar polynomial in the case of FQT T theta, which is this polynomial GT. And the GT is such that it's annihilating all the elements of FQ, annihilating in the theta sense, so in the skew sense. And you can remark that this polynomial is smaller degree than P. I mean, P minus 1 n plus 1 is smaller than Q, right? And it's normal because you have more roots. Okay, so let's go quickly. Now you can iterate array extensions. Here, since I have not too much time, I will just try to give you some idea. So this is the classical way of constructing an iterated array extension, and you can define there are two ways of defining the evaluation, and sometimes what is happening is that if you so the first way, you just you first, if you have to evaluate such a polynomial in A1 AN, you evaluate first you replace Tn by Tn minus An, so you evaluate at Tn and then you go down like this. The other way of defining or of evaluating is just to divide by the left ideal generated by T1 minus A1 plus T plus R, T2 minus A2, and so on. But this left ideal can be all the ring. So this is not a good way to work, but still you can do it. And you can do it with, as I said earlier. When you can practiced in both ways, they will coincide, and we call this a good point. And they are you replace your affine space by just the set of good points, so there are. Oh well, here I'm very quick. Yeah, we just applied this to the following question, and we get an answer. So there was a question by Werner about can you prove that if R is a finite ring, you look at the polynomials that are annihilating your finite ring, is it a two-sided ideal in your polynomial ring? Just usual polynomial with finite ring. The answer using the PLT is yes, but you can do it much more, because not only you can take a finite ring, but you can take a good ring. A good ring is a ring such that every element is a sum of units. For instance, you take every matrix ring over any ring. If you take an n by n matrix with n bigger or equal than 2, it's always a good ring. And we can do more than that. We can also go to sigma delta case. We can put many variables. All this, in all the cases, the Werner problem for finite ring in commutative setting is true. So thank you for your attention. I hope it was possible to follow. Thank you.
Thank you. Any questions, please? Thank you, Andrew, for this nice stimulating talk about solving the problem of Werner. Hope to have more and more on this later on.
There are a lot of things.
Yes, I know.
Yeah.
Okay, bye now. And so we now have a break, I guess.
Thank you, SK Jain sir, for chairing the session. So now we'll break for tea. So it's from 10:50 to 11:10. So from 11:10 we have second session. That will be plenary talk in the same venue. Thank you.
Okay, now I would like to put my laptop on the podium and then keep on moving and that's right. You are talking about White House at 2:50, 2 o'clock?
Yeah.
Right?
Yes, sir.
That will be, yeah, before that.
Yeah.
So then, it will be, you'll be clearing here, it is the last day. So you need to honor.
Hello.
After the talk.
You want.
Yeah, you are the honor, because it will be last steering and he has already finished the talk. Yeah, so there will be no more steering any other session. Okay, so you need to, I will honor after giving the talk, before giving the talk. After the talk. After the talk, I'll be ordering. Yeah, what for you, it will be later when you say that some another day.
You don't have any here. And we say important.
And you're getting a shock.
Yeah.
Yes.
Okay, so.
Very what?
Yeah.
It'll be better.
I wonder about.
If you'll be trading on the last day. Say one of the.
Hello.
Last
There will be.
Second. So, yeah. So we will see. Yeah.
Prasad, hello.
I think you can see. Yeah, let me work.
Is it there online? Is it available online?
Sir, I will check.
Yes.
Too many good questions.
You want to make some announcement?
I want to make my own announcement. Checking my.
No, he's not asking.
Just checking only, very, that is you were
Sorry. So,
If it's available, you
we have
could
not
check, you know.
yet
Just say thanks for joining us.
joined Iclaa, yeah, and if you this club, your steps also. Then the larger club is showing. And there will be understand.
Yeah, you get to view it as
In this club, we don't have.
oh yeah, first of all, don't need
Then there will be showing on in here. So that kind of thing, some restrictions will be there. You can say something like, you know, how to say something for this, so that is. We take a single ID go to maybe go to the. And this ID. You can come from the polynomial.
I take.
Some other ID might be. Somehow related to that, is there anything that must okay that some other ID will be related to, somehow they are related to that. And they are all in the yes. And then you can do something. This is my idea, I don't, I haven't seen any paper on this.
Yeah, I can make it bigger.
I think you have to type it,
So, I will be just doing myself.
Well, the activity in one of them.
Yeah. That's all right.
They all
Now, I know this.
I'm not getting some business.
You can
Something will be there somewhat. There. Not that, we could keep back and I don't know much about this advertisement. Maybe the, okay, so your idea about the minimum is interesting. So maybe the thing to do is, what if you start with a simple for what, by some miracle, the algebraic. With the simplest possible place to. See if you can use.
Maybe tomorrow I talk to you.
What you say?
Tomorrow I talk to you on certain issues, so, but I can, that's the.
There are no problem. There are no problem. Everything is fine. There are no problem. You are really doing great, excellent work. There's no.
There's definitely work on state transfer for
We have.
So,
before
last
last
week's
year, I- Let this show get good.
The Glasgow state transfer for special. So, but that.
Hello, is anyone there?
Yeah, understood.
Hello? Hello? No.
ಇಲ್ಲಿ ಅನ್ಮ್ಯೂಟ್ ಮಾಡಿದೆ.
Can you see me? Okay.
I can't hear you though.
Yeah.
Oh, I can hear you. I don't know whether you can hear me.
Yeah, now can you hear me?
Yes, yes.
Okay.
You can hear me too.
Okay. This sound coming from the. It is too noisy. Yeah. Thanks a lot for joining. It is a surprise for me.
Yes, I can't find a program. Is there a program?
I saw your mail very last minute, and
Oh,
I'm very happy, and immediately
No,
I
I read it
scheduled
here.
your talk for today. You want to say something?
I'm reading it here.
No problem, no?
You can reduce the.
Okay. So we missed you. Your physical presence here, we are missing, or you have come online. So for that, I'll have to say thanks to you.
oh, well, thank this. No, of course. You've
Uh,
always been very kind.
Anyway, next
And
time.
and one day you deserve to retire as well.
Hope that next time we'll meet.
So how am I giving my talk? Should I just share my screen?
Okay.
Yes.
Now people have gone for tea.
Yes,
Now,
when they come back.
Yeah, 11 o'clock. Where am I?
I think it was 11. Yeah. No, they'll be back shortly, but
Good.
all right. So I'm just going to share my screen and you can and
Now what is the time? Time must be 11:02 now. In
yeah.
about 10 minutes we'll start.
No, that's all right. That's good.
You can try whether you can share if there is any
Yeah.
problem or not. Yeah, there is no
All right.
problem. Your screen is
All
on.
right. Well, I just want to do one more thing.
Tell me.
I want to I'll do it as a full screen for a minute. Hold on.
Control L.
So I was going to stop. I'm going to stop and then start again.
Control L.
No, he's using
No,
PowerPoint.
it's all right. I'm just using PowerPoint at the
PowerPoint
moment.
F5.
Oh,
Yeah,
fine.
hold on. So what I'm going to do is, sorry, view. Oh dear, where we go?
So you will have to share the screen and press F5.
Yeah. Sorry, just a minute. Well, I'll try F5, but I don't think that works.
No,
on
you
my
will have to
machine.
share the screen first.
No. Hold on. Oh, where's it gone?
Earlier it was there. Your slide screen was there.
Yeah. Well. Oh, I see what the problem is. Sorry. Problem. Oh, no. Where's full screen gone?
You'll have to go back to Zoom.
I think he closed it. Ah,
Very odd. It was there 2 minutes ago. Hold on. Here we go.
Maybe you have closed the sharing part. You'll have to share again.
Yeah, well, that's right. Hold on. All right. I'll have to do the share first. Yes.
Yes, I see the message. Now you are sharing.
Right. So how can I get that onto so it occupies the entire screen? You think
Yeah,
F5?
Maybe F5 for full screen.
yes, F5.
Yeah, it doesn't work. Hold on.
F5 doesn't work.
You have to click on the slide once and then.
You'll have to click on slide.
Yeah, the problem is it's slide. Oh, here we go. I might just get
Slideshow
to
is
it.
there on the top.
Yeah,
Okay.
that's right. It's all right. I can just get to it. That's good.
Yeah.
All right. Thank you very much. You've done a wonderful job getting me organized.
Wonderful.
Now,
Hello. Tell me.
all right. So I just have one other request, which isn't directly related to my talk. Is there a program? Because I can't seem to access it. So I don't know when the talks are on. Other talks are on.
Program schedule. Sir.
Huh?
The program schedule he wants.
Yes, yes,
Like
please.
that.
Could somebody give me a link or email it to me or something like that, please?
Okay. At least you tell me what is the duration so that I can share it with you. Now, in very shortly, your talk can start. What is the time? And I have kept 40 minutes for entire talk, including 5 minutes of questions and answering.
About 35 minutes then.
Yeah. Shortly, audience will be coming. They have gone for tea.
No, when you're ready, I'm fine.
Kirkland is the person who will be chairing.
Yeah, well, I see Seymour has turned
He's
up.
also he will be coming. He will be coming and introducing you. And
Oh, I see.
he will be organizing this particular session.
Okay, thank you.
Anyway, let me express my gratitude to you. Thanks for coming and joining us.
Yes, well, I'm very sorry we could not come.
Towards the end, I may have to rush for something else. So I want to talk to you before that.
Okay.
Okay, we'll be in touch. Maybe other people will be coming now. With the Kirkland again, is it on time?
He just went out 5 minutes ago. Yeah. It's still 3.
Still 5 more minutes are there. You can relax and wait for a few minutes. Thank you. Okay.
Oh. How come?
Did you log in here?
Oh, it auto locked in.
Krishna, what happened to you? Nothing happened.
ನಾನು ಹೊರಡ್ದೆ ನಿಮ್ ಜೊತೆಗೆ ನಾನು ನಿಮ್ ಜೊತೆ ಹೊರಡ್ತೆ ಗಾಡಿ ಚಾರ್ಜ್ ಮಾಡ್ಕೊಂಡ್ ಬರ್ತೆ ನಾನು ನಿಮ್ ಜೊತೆ ಹೊರಟು ಸ್ಕೂಟಿಯಲ್ಲಿ ಗಾಡಿ ಚಾರ್ಜ್ ಮಾಡ್ಕೊಂಡ್ ಬರ್ತೆ ಅಂತ ಹೇಳಿದ್ರು ಅದನ್ನ ಮಾಡ್ಬೇಕು ಕರೆಕ್ಷನ್ ಅವ್ರು ಕಳ್ಸಾರ ಮೇಲಲ್ಲಿ ಕಳ್ಸಾರ ನಂಗೆ ಧನ್ಯವಾದ ನೋಡ್ತೇನೆ ಸರಿ
Greetings, Simo.
Said something.
Yeah, sorry. What did
He
you
said
say?
something.
Sorry, pardon?
I just said hello to Simo.
Ah,
We try to bring him,
he's here. He's here.
huh?
He's here
He's already there.
in the meeting, yes.
And on the screen, 5 minutes, yeah. Ah. Where? Mike. Hello. Timo.
He's not unmuted.
Huh?
He has to unmute himself.
Timo, you
Oh.
are.
Yes. Now we can hear.
Oh,
Yes.
we've got a larger proportion of Simo now.
How are you?
I'm all right. I'm just woke up.
In your absence, I have kept your schedule.
When is my talk to be given?
So I have kept it. You don't have to go by that schedule. But I wanted to invite you to join us before valedictory on Saturday.
Saturday, fine. Yes, Saturday, fine. Yes.
After what time?
Oh, anytime I'm available.
Yeah, around 4 o'clock Indian time in the evening. Before valedictory, I want you to join us and speak for a few minutes.
Okay.
Remember, don't forget.
Okay, fine. Remind me by email.
Yeah, I'll write to you. And since now you are available, I'm
Yes.
inviting you directly. Yeah? So we missed you again this year. Hello, is it off? Gone off? It has gone off again. Hello. Hello, can you hear me?
You mean
Mike
me?
Yeah. Mike has gone off again. Okay.
Fine.
Forgot what I was trying to say. Yeah, we are missing you again.
Yes, it was quite something. Well, that's all I can say. Anyway.
Maybe next time I'll force you to come on my personal invitation,
Yes.
if not for academic activity.
Okay. Yes. Please, I definitely want to see you face to face.
Anyway, I was also happy to see Mika.
Oh,
So,
good. Yes.
in fact, I have given your slot to him.
Hmm.
That talk schedule. In the talk schedule. I have kept you in your place. In the invited session, I have kept him.
Yes.
So
So,
when are you talking?
his talk is scheduled tomorrow. Mika.
No, when Simo's talk
Is it
scheduled.
today? Today, Indian time, 3:45.
3:45. Okay.
Yeah, 3:45. Okay, Steve Kirkland is with us now. Can you focus it? Okay. Now he'll take over as a chairman of this session.
Hi, everybody. Welcome back from the tea break. So it's my pleasure to chair this session. Our speaker is Stephen Haslett from Massey University in New Zealand, and he's going to tell us about the effects of transforming genetic relatedness matrices on linear mixed models based quantitative genetic analysis. Stephen, take it away.
Thank you very much. It's very nice to be here, even if only virtually. This talk began because somebody came to see me about a problem, and it turned out that the problem was related to something I knew something about, and that's always a very nice experience. But what I'm going to do is to give you a little bit of background on what quantitative genetic analyses are and why this is a why this is quite an important problem, in fact. So often with these quantitative genetic analyses, they use linear mixed models. And the idea is we're connecting an observable trait, like it might be hair color or something similar, to a series of fixed effects using random effects that reflect the relatedness among the individuals, because the individuals are related to one another, so the observations are not independent. We've also got an additional non-genetic error, so you can start to see how this links to a linear mixed model. I'll give more details shortly. And much of the statistical methodology was developed in the context of plant and animal breeding. And the point about this is the coupled individuals or the sampled individuals were for controlled crosses, and the relationship was known. So when you're breeding plants and animals, you can decide which you're going to put with which. But for natural populations and even for breeding programs where pedigrees are not known, this relatedness has become more of an issue. And particularly when people started using extensive genetic marker information to in the form of random effects. So we're going to look at the effect on fixed effect regression in a linear model, where we've got this measure of relatedness, which is a genetic relatedness matrix, but we have to transform it because the original form, in its original form, it's not estimable. So this falls back to or links back to an old problem, one of CRR's, where we're looking at part of it does at least, we're looking at necessary and sufficient conditions for retention of all the best linear unbiased estimates of functions of estimated fixed parameters under changes of covariance structure. CMO will remember that this is a topic we have talked about at length. So the point is that neither G nor K, which we're going to talk about shortly, which are these genetic relatedness matrix or the kinship matrix, they're not estimable. But particular transformations of them are, and we're going to talk about those transformations and how it affects the estimates of the fixed parameters. So the ones we're going to talk about are called allele sharing and Popkin and standard. I'll explain what those are shortly. And we're going to particularly focus on the design matrix with X as full rank in this talk. I'll touch upon some other situations, but the reason for this is that what usually happens is the design matrix consists of a vector of ones corresponding to the intercept. And then each SNP is put in one at a time into an X matrix. And there are often millions of these, so we're fitting millions of models. So the emphasis often in this stuff has been on computation rather than the linear algebra. And you're also going to look at a situation where we've got retention of only the non-intercept estimated parameters or estimable functions of them, because this is used in what's called the standard estimator. And this is what's often programmed in packages that are run very efficiently to try and sort through millions of possible SNPs or pieces of DNA or genes that might be responsible for a particular trait, or like hair color. There are some further results which I'm not going to cover in detail, or not really cover them at all in this talk. But we can also look at retention of sums of squares, various types of basic residuals, and particular submatrices of the covariance of the blues. And we're just people who are actually aware of what's going on here. It turns out that estimation of the ancestral population heritability is not possible, no matter what we do. So what I've covered here is the abstract. I just wanted to mention that it's Bruce Weir and Jerome Goudet. Bruce is at the University of Seattle and back in New Zealand, and Jerome Goudet is in Switzerland. But they're essentially geneticists. Bruce, although they're both statisticians, their focus has been much more on the genetics aspect of this. I'll skip over the keywords in the AMS, but I do want to emphasize that this all comes back at some point to C.R. Rao's paper in Sankhya in 1971. This slide, I'm not going to focus on for very long. I just want to emphasize again that we're looking at blues. We're not so much doing BLUP in this case, because although we've got random effects, we're not trying to predict the random effects. We're interested in trying each SNP or single nucleotide polymorphism one at a time in a regression model. But we've got the complication that there is the covariance structure for the error is not IID. So there's all sorts of techniques that have been used as G-BLUP and multi-BLUP, and Reynolds used quite frequently. And they're used in a wide range of things in genetics, and association mapping, genomic heritability estimation, detection of inbreeding depression, quantitative trait analysis, to give an example. And this, what's on the remainder of this slide is really about how many SNPs there are. So there's an example here where there's nearly 4 million SNPs, which would fit 4 million models. And each of these models is not small, because we've got, in that case, we've got quite a number of individuals. But the top mid program has 380 million SNPs. So that's 380 million models that we need to fit to nearly 54,000 individuals. You can see the computational part of this is tended to push the types of statistics that are done. People are have been much more concerned about efficient algorithms than they have about the linear algebra behind it. All right, so the point is, as I've said, if every SNP's treated simultaneously as a fixed parameter, we don't do this because we have put them in the random effects, because the number of parameters would then greatly exceed the sample size. So instead, what we're doing is we'd like to use a genomic relatedness matrix or kinship matrix, and it's important to emphasize where you see G, it's just equal to 2K, basically because there's 2 chromosomes of the same type in a diploid individual. And the kinship K involves the probability a random allele for an individual is identical by descent. I'll give some more details of that shortly, but this is not entirely the point. The difficulty is that identical by descent is not estimable. So if we had the kinship matrix or the GRM, genetic relatedness matrix, what we do is we're going to scale and use them as a random effect in this model. I mean, the classical work for this was done by Henderson, but as I said, with the genetic data, we can no longer get a handle on K or G. We have to use transformations of them. And the question is, under these transformations, which properties are retained as if we had been able to use K or G? So Rao's results look at leaving all of the blues of an estimable linear combination of fixed parameters unchanged when we change the covariance structure. So what we're looking at is rearrangements of this G or K matrix, which in turn changes the overall or total variance covariance matrix. And what we're asking is, do we still get the same fixed parameters and various other properties as well? So we don't have any observation information about this identity by descent. And one of the unresolved questions, because it's used the thing that's used mostly is to take this GRM matrix and double center it, which makes all its row and column sum 0. So this is a standard kinship matrix, and I'll talk about the properties of that. It turns out that this matrix, this adjustment or this transformation doesn't work as well as 2 other possible transformations, even though it's the one that's written into enormous amounts of the software. So this is kind of a possible paradigm change if people will listen, because what we're basically saying is that the standard way of doing things can be improved. It's not that the standard one is completely wrong. It does allow you to get an estimate of the right estimate of the slope and an estimate of its variance. but that's the slope corresponding to the SNP, and usually it's the slope that is the most important. But more things are possible if we use another, if we don't use the standard one and use the other two estimators. So what I'm going to talk about quickly is what these genetic and kinship matrices are that we're using as a substitute. The transformations that we're using. So this is the allele sharing one. And the thing about it I want to just emphasize, there's quite a lot of material on this slide, but basically what we know at each SNP or at each location on the genetic material, where there's each DNA base, what we know is what is there. And these dosage, if we're looking for a particular allele, might be guanine or cytosine or whatever, but what we're looking at there is whether we've got on the two chromosomes, you've got 0 of this or 1 or 2. And those things in turn are used to actually look at two individuals collectively, and what we get is a value of 0 or 0.5 or 1. And these are these A values. Now that's quite important, and you know the point about this is that we can look at what the asymptotic thing says. And the important equation here is not equation 1. For those of you who may want, you can read through the rest of the material on the slide. The important thing is equation 2. And what that says is that KAS, the allele sharing version of K, is equal to this whole thing here. But the odd thing about this equation is KAS is estimable, but K and phi AS are not. So the odd thing is we can't get to K, but we can get KAS. And the question is, if we incorporate KAS into the random effects, are we going to be able to get out what we would have got out if we've been able to use K directly? There's another estimator, which is actually very similar in structure. You'll see that all that's changed here is that AS has been replaced by P. There's a side issue, which I won't go into, which under certain conditions it's not possible to test for. This KP becomes K because phi P is set to 0. Phi P is the minimum and it's possible to set it to 0, but there's no evidence that this is a good idea. So I'm going to focus on equation 3, and you'll see the form of this here is basically involves a scaling and a subtraction of a multiple of a matrix that's just made up of ones. So it basically is shifting the mean, or shifting almost shifting an origin. Now the next one is the standard estimator, and again there's a whole lot of material here, but basically the assumption is made here that the allelic doses that I talked about earlier are binomial random variables, but in a real population it's not true because there's inbreeding and co-ancestry. But the asymptotic version of this doubly centered version is K standard, and you'll see that it's here. I'll give another version of it shortly. Again, it's scaled, but basically it's the centering matrix times K times the centering matrix, again divided by this 1 minus phi standard. That's not the form that's written here, but I'll come to that. I'll write it out in the other form shortly. So onto some more familiar material, perhaps. What we're looking at here, what we're looking here is we're back to a linear model, because Rao's result applied to linear models, not to mixed models. So I'm going to try and link those two up in just a minute. But what we've got is we've got an error in here with the covariance that's V0. A lot of usual notation. V0's the covariance of Y. We've got expectation 0. X is a design matrix. Beta is the vector of fixed but unknown parameters. And sometimes we might use mu equal to x beta, noting that mu is estimable even if x is not full rank. And we're going to use this MV0 or MV to emphasize the relevant covariance matrix in this model here, which is MV0, which is made up of the Y and the x beta and the V0. So all of that's pretty standard. So we're going to denote, this is just notation again, we've got blue of mu given V naught, we've got the blue of beta. I'm usually going to suppress V naught because that's the thing that's got the blues. That's what we'd really like. It'll be the one using the actual the actual G or K, which we don't know. So it'll be implicitly to be the linear model with K and V naught. And I'll just use blue or blues where it's a shorthand will work, where I hope there's no confusion. So what we want to do is compare this MV naught with a model changed, except that its error of variance covariance is V rather than V naught, and ask what conditions the blues will remain the same. All the blues will remain the same. But we'll also consider retention of a subset of mu or a subset of beta, because that's what will happen if we use K standard. And what we find is that we can't get the blue off the intercept, which we can with the allele sharing and pop conversions of K. So what we've got here is the covariance of E, if we actually were able to get hold of it, consists of sigma squared G plus sigma A squared G plus sigma E squared I, or this equation down below. Apologies for the double equal sign. So the point is that we know what this covariance is, or we'd like to know what it is. We don't actually know sigma squared A, we don't know K, we don't know sigma squared E. So what are we going to do? Well, we use one of these two forms here. We've got KD is equal to this for the allele sharing in Popkin, where we basically are subtracting off phi d times j and dividing by 1 minus phi d. But the point is that we do know KD, we can estimate KD, we cannot estimate K, we cannot estimate phi d. And for the standard estimator, what we get is this thing here. You can see it's basically this centering matrix times K times the centering matrix, again divided by something we don't know. So we know this, we don't know K, and we don't know phi standard. Sorry, is somebody have a question? I can see someone talking. Anyway, the point is that the V that we now want is this here. It turns out that V that we want, we know KD, and we can actually work out what V is for these estimators. Now it's got a multiplier, and this multiplier here, 1 minus phi d times sigma squared A, is important. I'm not going to go into a lot of detail on that. It's just really I'm going to try and focus on the V's. So the SNPs actually, one particular SNP, chosen SNP, makes up the rest of X. The other part of X generally is just the intercept term. And we try millions of these SNPs one at a time. So if we wanted to view it in another notation, we've basically got a linear mixed model. And the way we're getting V naught is basically to put together all the error terms and focus on our estimation of the fixed effects. So that's just a fairly standard way of writing out the linear mixed model. Notation. Well, we're looking at ranks, and we're looking at generalized inverses. We're looking at more Penrose inverses. We're looking at column spaces. And we're looking at the space that's perpendicular to the column space of a matrix A. We've got transposers. I won't be using QA very much. I will be using M, because the point is that X times X perp is equal to 0, and we can substitute X perp. M is, in some sense, it's equivalent. So X times M is 0. They're orthogonal subspaces. Now, the important equations from Rao are these two here. So basically, the V that works consists of the original V naught. It may be scaled as it is down here in this second in equation 20, but what we can add on is something that's in the column space of X, or something that's in the column space of V naught times M, cross product terms. So what we've got is this equation here, but we find that in the situation that we're dealing with, it simplifies enormously. We're looking at matrices that are, or design matrices that the only thing they have in common is that they've got a column of ones. So all of this simplifies. It simplifies considerably because we're not allowed then various types of terms. I've outlined just why in the first paragraph there. And basically the only thing that's going to work is V0 plus Bj, where B is a scalar. And you'll see that this has strong links, particularly when we add in an A in front, as we do in this equation, which is still permissible. You'll see this looks remarkably like the sort of equation we were looking at for the allele sharing and Popkin estimators. So this is why, for the Popkin and allele sharing, they conform to the requirement. Sorry. Sorry for the delay. All right. We were able to show that Popkin and allele sharing conform with Rao's requirement, but the standard estimator doesn't. So the important thing here is that we can't actually estimate V0, but we can estimate V. So being able to keep this property and still get the blues is a somewhat surprising result, because K is inestimable. We only know KAS and KP, but it turns out that if we use either of them, what we get is exactly what we want. We get the blues as if we knew K. All right, so if we're using the standard estimator in Rao, you're using the double-centered version of K or G. We can't get all the functions of estimable parameters of beta, but it turns out that we can get something out of it. What we can get is some of the blues are retained, particularly the slope or anything that's not the intercept. If we've got more columns in X, more SNPs being looked at once. It also turns out that we can also get the variance of the blues for the slope, the correct variance of the blues for the slope. So what we've got is that we've got random effects. The random effects use K, and if we use K standard, we can retain the same blue for the slope and the variance of the blue of the slope, but the parameter estimate for the intercept is wrong. And just to complete, what I'm going to do is sort of go through and just sort of show you how the proof works, because it's quite interesting that, I mean, Rao's paper is very much about retaining all the blues, but it turns out there are conditions under which you can retain some of them. And further work that I've done with Simo and Augustin and Jaco have shown that actually we can work out ways of getting back some of the covariance properties of the blues, and also the sums of squares of errors. And it turns out we can do quite well with all of these, better with the allele sharing and Popkin than with the standard, but still we can do well. So I just wanted to look at this business of what happens when we've got the standard estimator. So the V0 that we'd like but can't use because we don't know K is here, and the V that we're actually looking at if we're looking at the allele sharing and Popkin, which I'm just going to put to one side for the moment, would be this. But the V for the standard estimator is this one here, and it turns out that it's equal to this: sigma squared A C star K C star plus sigma squared EI. And the only thing that's different in this is that this centering matrix, C star, K, C star, has replaced K. All right, so C star as the centering matrix is defined here, and all it's really doing is subtracting 1 upon n from all of the elements of C. Well, C is a diagonal from all the elements of I, where I is the usual diagonal identity matrix. So for this model, I'm going to split X into the column that is for the intercept and the remainder of X, which I'm going to call X with a small x subscript. I'm going to do the same with beta, and we're going to look at a more general partitioning initially, which is in Simo and Jaco and the book tricks, and it basically comes out in this. I'm sorry, there's a 1 missing on the X here on that X. But basically what it turns out is that this matrix M1, which is actually the orthogonal projector, which is orthogonal to X1, curiously just collapses and turns into C star. And this is the key for why this works. So the first thing is that M1 times C star is equal to M1 times the centering matrix here, which is equal to M1 times this here. But the point is that this second term is 0 because M is the column space of M is the same as the column space of M perpendicular to X, and J belongs to the column space of X. So this product here is 0, and M1 times C star equals M1. Key. So when we're looking at this function here, which has a familiar structure, if we're looking at residuals, and is equal to this here, what we find is that what we get is for V naught actually has the C star reappearing because C star is equal to M1. So what we get is here. And C star is symmetric and idempotent, so C star equals C star transpose. If we multiply it by itself, we get C star again. So I just want you to look at that M dot there for a minute for V naught. And now when we look at what happens to the standard estimator, we go through the same exercise. V standard has been replacing V naught, so we've got a C star and a C star here, where previously for V naught we just had K. But all of this seems to disappear because C star times C star is just C star again, and this C star times that one is C star again. So M1 dot for V standard is the same as M1 dot for V naught, and when we put it into this formula here, what we find is that this expression here is actually equal to, they're both equal to one another. So we can just call it M1, and since the blue of the non-intercept parameters is under V naught is equal to this, we find that it's actually equal to the estimate of the non-intercept parameters using V standard as required. So this isn't quite down the same line as Rao's 1971 proof at all, but it does turn out that some of the parameters are going to be retained. And it also turns out that we can also retain, if we're careful, we can retain the error sum of squares for all of these estimators, for the allele sharing, for the Popkin and for the standard one. We can retain, as it turns out, the conditional residuals, which are used in deletion diagnostics. We can retain in the case of the allele sharing and the Popkin estimator, we can retain all of the covariance structure for the blues except for the variance of the intercept. And in the case of the standard estimator, we can retain the covariance of the estimates of beta x, the non-intercept parameters. So there's an enormous amount. Although we cannot estimate the kinship matrix that we'd like to estimate, it's inestimable. Even by using these transformed versions of K, it's possible to get out nearly everything that we could have got out if we had known K. So thank you very much.
Good. So we have time for questions or comments. Okay, I have another medical question, and I'm going to put you on the spot a little bit. Some of the underlying theme here is the impact of Rao's work. What are we talking about, 50, 75 years later?
That's right.
Do you want to maybe talk about the ripple effect of his work on yours?
Well, the short answer is considerable, at least in this area. I do work on small area estimation and design of sample surveys, but you know, I've been fortunate that George Stein and Simo have been willing to talk to me for years. So I think the important thing about this is that, I mean, these results have been used in other places, but this whole area of genetics, where these results are clearly very important, it seems that nobody in the whole genetics area has been very aware that Rao's work has got any implications for them. And because they're so focused on the computational problems, every now and again, one of these things pops up. They use one of the estimators and one of the others, and they find they run a simulation where they do know K, and they find they get the same blues, and they don't know why. They haven't been aware why. So it was just fortunate that Bruce came back to New Zealand. He's retired and come back to New Zealand. He's a New Zealander. And he was looking for somebody who might know something about this. And it turns out that that I just happened to be here. So he ended up talking to me, and I said, "Oh, but I know the answer to that problem." So we've been. Well, I didn't initially. I think we've spent some months working through the questions that he's got and the results. But I think it's a really nice application of CRR's work, and I think it may turn out to be very important because it's not just for human population studies this is relevant. It's also highly relevant for getting out best animal breeding properties and plant breeding properties, and possibly getting out better estimators. I'll stop there.
Very good, thank you. We should be telling our deans and our directors about the long-term benefits of investing
Yes,
in
this is the
mathematical
long-term
sciences.
benefits of theoretical research.
Absolutely.
Yeah,
Thanks very much, Stephen.
Yeah.
Okay, and I think we have a break for lunch, is that correct?
No, sir.
Oh, thank you all very much.
Thank you, sir. Thank you, Professor Stephen Hasler, sir, and thank you, Stephen Iclaa, sir, for chairing the session. So next session is contributory talks. It will be starting from 12 p.m. to 1 p.m. at Academic Block 3, the same venue in NLH. And the sessions are actually chaired by, first one is Professor Rajesh Kannan, sir, at 203 room, and Vinay Madhusudan, sir, at room number 202. And KB Srinivas sir at 204, and Srimati Maya ma'am at 205. And from 1 p.m. to 2:10, it's a lunch time, and from 2:15, we'll have plenary talk by Professor S.K. Jain sir in the same venue here itself. So I want everyone to join at 2:15. So now we can move to the NLH. Thank you.
Yeah, we'll go. Yes. Yeah,
I'm checking my emails. I think,
Oh, okay.
give you an